Good evening, everyone. Probably good morning in the UK. Um, yeah, I changed my title to a high performance piezoresistive sensor for epidermal pulse monitoring. First of all, I have a very brief introduction to our laboratory. This is a wearable materials for healthcare established in the City University of Hong Kong last year. It's located in the biomedical engineering department. The City University is a very young university, but it's ranked very high. It's the number one most international university in the world. It's number four in top 50 university under 50. Um, before before I came to CTU, I was working in Hong Kong Polytechnic University, where I had basic research areas as represented here. Um, since last year, I moved to the City University. As I said, I established a laboratory for of wearable materials for healthcare. We have three areas of research: changing medical energy therapies, shaman materials, biomaterials, wearable materials, and textile electronics for healthcare and beauty care. Maybe I make a little promotion marketing here. Yeah, we have PhD fellowship. We have Hong Kong, uh, uh, yeah, Hong Kong PhD fellowships, EDU PhD scholarship, and doctoral fellow positions available. Okay, let's come to the to the contents for today's lecture. Um, yeah, we have been using textiles for wearable electronics, and today's topic is using textiles for wearable electronics. So first of all, let's see what textiles for wearable electronics. Wearables, everybody have every day. These are wearables, traditional wearables for protection and aesthetics. But now wearables have more functions. One of the functions is to use for healthcare. They can be used for example, massages, signal monitoring, diabetics socks. Um, yeah, this haptic clothing, wound care devices, etc. The extension of that healthcare function of wearables, particularly clothing, is the can you see is the inclusion of various sensors, and which can be very well integrated into clothing, and this can be used for also healthcare monitoring many. And these mainly use the textiles. The sensor is inside the clothing, can be textiles, can be partially textiles. So wearable electronics have been extending to more functional, more user-friendly electronic field. And wearables can also refer to the to those sensors which can be directly attached to our skin. There are some very frequently studied locations which can be used for putting sensors, even actuators. Um, so as a whole, wearable electronics, wearable materials have been, electronic materials have been developing for the past maybe several decades. At the beginning, yeah, we used the scientists and commercial devices, commercial product use hardwares. The hardwares can be wearable for the for some purposes. For example, you can put a camera on your hand. You can can put a glass on your yeah, on your eyes. But this is very hard. These are not very user friendly in many ways. So it comes to the flexible wearable electronics become the second generation. They can provide a lot of convenience and comfort. So these are some examples. And after that, because flexibles can actually stand bending deformation, but they cannot be stretchable. So stretchable become a later generation, but even this kind of uh, materials are not sufficient for meeting all the requirements of the wearable electronics. So textiles and textile-based wearable electronics become the trend. Even the top scientists in the wearable electronics field now start to use textiles. This is because textiles have many advantages. In addition to stretchable and flexible, they are very strong. They are durable. They have hierarchical structure. They have lightweight, particularly air and water moisture permeable. This is very important, and they are also biocompatible. So textiles have become the frontier, come to the frontier for wearable electronics. So why fibers and textiles? Why we use textiles for wearable electronics? Here shows the structural principles. Actually, these kind of structures provide sleepability, provide a relative movement between the fibers, between the yarns. This can you see, and this kind of interlacing, these looping structures can allow the pores to exist. So this can provide the properties we mentioned in previous slide. Specifically, can have the flexibility, stretchability, and the porosity. Another thing is that textiles can have very good conformability. That means they can fit into different kind of structures, three-dimensional structures without any wrinkling, without any sharp edges. They can also be draped. Textiles can be made into hierarchical structure. They are naturally hierarchical structure. This kind of hierarchical structure can provide a lot of good properties for wearables: fit, comfort, stretchability, flexibility, porosity, connectivity, continuity, and high surface area. So these are the reasons for textiles be used for wearable electronics and become the frontier of wearable electronics. Another thing is that textiles have helical structure. Helical structure, you can see we do not um, adhere the fibers together, make them very rigid. Instead, we twist them together. So fibers have the cohesion with each other. At the same time, they can move relative to each other. So this kind of structures can provide strength, porosity, and the flexibility. So textiles can be used for wearable electronics because they really fit the human physiological and even about physiological and psychological requirements. Um, and actually, textiles have become very important, and a lot of people are aware of its advantages. Um, because of the technologies available, it has gone through this kind of evolution. Okay, in the past, we used the hardware to just install it or integrate it into the textiles in this way. And currently, there are textile integrated electronics, but tomorrow or starting from today, there are pure textile, whole textile, or all textile in electronics. So if we look at the fiber development, we have gone through this kind of paradigms: natural fibers, chemical fiber, functional fiber, smart fiber. This can be widely used for wearable electronics. And the wearable electronics using textiles can be used for any harvesting, health monitoring, safe protection treatment, monitoring, and others. Um, yeah, so we have been discussing textiles for wearable electronics and its importance. Um, in terms of applications, healthcare is one of the very important, most important field to use textiles. And healthcare is related to our health, our body. So the wearables can provide a lot of advantages. Okay, we have reviewed the textiles as wearable electronics. Now let's look at one of the applications of textiles. Actually, here for traditional Chinese medicine, in particular for post-diagnosis. Let's have a little review on traditional Chinese medicine post-diagnosis. You can see this is a very traditional way for Chinese doctors to diagnose, to do the diagnose. Here is the basic rules. They put their three fingers at these three positions, and then these three fingers can press to different levels. Namely, they have three levels, and uh, on both hands, the doctors can do the diagnosis for different for different organs. For the right wrist, there are these are six organs associated. If you press superficially, you can diagnose these three organs conditions. If you press deeply, you probably can feel the problems, the conditions of these several organs. For left wrist, the organs are different. So altogether, probably this can be considered as the sixth systems for Chinese medicine. Through the diagnosis, the Chinese doctors, traditional Chinese medicine, has classified, has some classifications for different types of poses, which are related to different health conditions or diseases. In particular, they have this kind of classifications. For you can see this kind of poses are many um, on the surface. You can feel it very easily, but they many existing on the surface. And here there are many at the bottom, and here probably normal circumstances with the positions, but the the post patterns have some broken lines, and this is a condition of the weakness of health conditions. You can see these poses are not continuous or not strong enough or not very solid. But for this one, in contrast, the poses are very strong or very solid or even very thick, and this probably similar, but with this can be run faster than this one. So they classify the poses into different groups. Here is another type of classification of poses. They have six categories: floating on the surface, deep on the bottom, empty. That means the poses seems to it's not very solid, and slow and very rapid, and even for this similar to this kind of pose, they can also be classified into subcategories. By using different kind of poses. This is classes, categories, 1, 2, 3, 4, and this representing this is the pose name, this is the pose patterns, and these are the diseases. They make they make the pose patterns related to to different types of diseases or health conditions. Altogether, for Chinese medicine, and there are 28 types of poses. They representing different types of health condition. Okay, in order to get this kind of signals of poses on the wrist, we have developed a pressure sensor for traditional Chinese medicine post diagnosis. It is actually now online in advanced materials. Okay, here is the design of our textile sensor. We, here is the fabric. Here's the fabric, knitted fabric. This fabric is using this kind of double helix yarns. In particular, this helix yarn has a structure similar to DNA, and this yarns using fibers of nylon, which has a core shell structure. In the core, we use the nylons, and in the shell, this is a coating of copper nanoparticles. And by using this kind of yarns, we can make these fabrics, and this can provide us sensoring functions. And yeah, particularly we use this kind of yarns, and this kind of yarns are actually made by two yarns, and these two yarns are twisted together to form a double yarn. This is the yarn structure. Here you can see this is the yarn structure. We have been using this this type of yarn for this type of knitted fabric. After the fabric, this is actually conductive fiber, a conductive fabric, conductive textile, because fibers are coated with copper. Copper is a very good conductor, so it can conduct the electricity. So we use this fabric here to make a sensor. This is the electrode. This is the protection material, and here is the sensor. So the sensor is totally flexible, is also very durable. Here is our sensor, and it's made by the methods described here, and we can rolling it, we can squeeze it, we can twist it. So this means our sensor is very flexible. Here is the fabrication process for yarn to fabric. Here is the machine. We have two yarns doubled together. We can make the yarn like this, and then we use this machine to make the fabric. And here's the fabric. Here are the fabric. This is the fabric for connection. Okay. After the fabric is made, we investigated pressure current relationship for different types of yarns. Here we actually chosen two types of yarns. One is untwisted. This is the material quantity and basic structures are exactly the same, but this one is DNA like a yarn. We have made two single yarns twisted into a double yarn. So this now let's compare their pressure current relationship. Now this is untwisted yarn, this is twisted yarn. You can see if we apply the pressure up to 800 Pascal, and you can see their structures are very different. Their stress strain curves are different. The difference is that this one you can see is not linear. This is more linear. This is not linear. Again, this is probably, you can separate it into two sections. They can be probably approximated to linear. However, this is much more linear. The first thing. And secondly, if we take this small part, for example, here is 20, 30. Here's a 30. If we take this small part, if we take this small part, for further analysis, you can see the stress and curve very scattered. We repeatedly testing it. You can see the stress strain curves cannot be repeatable. But instead, here, if we use the DNA-like twisted Yangs, you can see no matter how many cycles we do, the current pressure relation is still very linear and without too much hysteresis. We consider this is a very reliable structure. So we adapted this Yang for making a piece of fabric for textile sensor. We compare two types of the Yangs presented in the previous slide. We can see that the hysteresis and twisted Yang, you can see cycles. They're quite consistent, and twisted Yang has very little hysteresis. Is around 5%. So it's almost negligible. But for the you can see the variation. Twisted Yang has very big variation. This variation is still also very big. This is in terms of here in terms of linearity. Linearity here is it's smaller. It's good, I think. And then we tested the sensitivity of detection of our sensor. We use the grain. It's a rice of 8 milligram on the sensor. You can see it can feel the loading. You can feel the loading very regularly and regularly, steadily, and very rapidly. And we also tested the response time. That means how long does it take to detect the signal correctly and accurately. Here we magnify here. You can see from this state to this state only 2 microseconds. When you retest to this to another state, it also takes 2 microseconds. So we also tested the durability. We tested here is 4,000 times. This is 6,000 times. Basically, it is with different level of pressure. Basically, you can see they do not have too much difference from very beginning to the very last. Here is also the same from very beginning to the very last. Their wave patterns and the wave structures are almost exactly the same. Okay, we also measure the mechanical properties of the two types of Yangs. You can see this twisted Yang has a much better strength and strain, so it can be much more durable. And the tensile strengths here, tensile strain, and certainly the twisted Yangs are superior to the untwisted Yang. So now, after we examined the reliability of our sensors, we applied this sensor for measuring the pulses of wrist at 3 places, 3 positions. This is one, this is two, and then this is the two corresponding to these 3 positions. And you can see from here, they have different, they do demonstrate different poses, different patterns. And also, this can be repeatable. The first time, second time, third time. They are this representing also different levels, different pressures of the the pulses from. After all, we define an index. We've defined the index to compare our sensor with the existing reported work. These are different samples from different publications. Here is ours. What does it mean here? You can see here the response time. We saw that we only our sensor only takes 2 milliseconds. So this is a very, very quick response. At the same time, the recovery rate, the recovery time and the rate is very, the time is also very short. You can see this is our sensor has the shortest response time. These are the other publications. We yeah, we did some comparison um, of two people. Actually, this is normal person. This is a person with sinus bradycardia. You can see their pulse patterns are different. Um, yeah, we have put some biomarkers. You can see a normal person. They have this value, but with this sinus bradycardia, this value is very high. So this we can differentiate. That means this sensor can differentiate the different the human body conditions. We did a serum analysis for explaining the robustness of our structure, and we also did some more detection, post detection, for people before exercise, after exercise. You saw this before. We can also measure the pulses at different positions of our body. For example, we can measure leg, we can measure a wrist. Yeah, here we have put all related information here. So in general, we measure two pulses, two arteries, the pulses of two arteries. One is here, one is here. We also did the pulses detection before and after exercise. Here is saying the quick response. Here is saying the durability. Here is saying the response to different pressure, different types of voltage. Okay, we have just published this paper in Advanced Materials. In fact, this is a starting point. We still have a lot of things to do. The first thing is that we have to do the data connection and do the analysis. Only we get a huge data or big data, we can do the feature extraction, model training, and then hopefully we can classify the pulses into different categories, just like Chinese medical doctors have made the classes, and then we need to learn from the doctors and to diagnose that monitor and diagnose the human body conditions. First thing we need to do in future. And secondly, we are planning, actually we have been doing self-charging power system, because the pulse can provide some mechanical energy. Hopefully we can harvest this kind of energy to work with sensor, so the system is powerless.
Professor Wu, is it
Okay.
we're coming towards the end?
Okay,
Now,
yeah, come to the end. We
okay.
have the electro system. Here's
Thank
the
you so much.
conclusion. Yeah. Okay. Yeah. This is what we are going to do in future. Okay, that's the end of my presentation. Thank you.
Thank you very much. That's brilliant. We have time for at least one question. Does anybody have a question in regards to this talk? Anyone? I just have a quick question. What
Yes.
companies are interested in taking this on? Are you engaged with any companies to commercialize this technology?
Not yet. We just published this paper, and actually, our university has supported our students, a group of
Yes.
students, commercialize it by ourselves. Yeah, we just started.
Okay, it looks really quite exciting. I have to say, I didn't realize you can get so much information about your organs from sensing your wrist. I found that actually intriguing. I guess that's all Chinese information, I guess, is it, from coming through?
Yeah, the Chinese, Chinese doctor normally a small pillow, a rest pillow is their whole facilities, the whole clinic. So they can rely on this kind of diagnosis for judging the patient's health condition. Yeah, they have the series for doing that. Each point is associated with organs. Actually, I think it's a system. The organs are connected by the meridians. Meridians are connected by the acupoints. So it's a huge system. We need
It's
to figure
amazing.
it out.
Any other questions? Well, thank you so much, Professor Hu. Thank you.
You're welcome. Thank you.
Right, we actually break now for lunch. We return at 1 o'clock, and there'll be a new chair, Dr. Zeo. So thank you very much this morning. I've enjoyed it. I hope you've enjoyed it, and we'll see you at 1 o'clock. Thank you very much.